Hello, thank you all for joining me today for my flow simulation presentation. My name is Alec Cook. I am an application engineer with GoEngineer. Let's get started since we have a lot to cover today. When I was working towards my degree for aerospace engineering, I was introduced to the Magnus Effect, which led me to this idea where I can replace the leading edge of a wing with a cylinder that rotates. I mentioned this idea to my old professor, and he showed interest and he said it could potentially solve leading edge buildup on a wing during winter. And then he also wanted to take a look at the effects the cylinder had on a wing in regards to lift and stall angle. And I'll explain why I came up with these different Reynolds numbers to first test, and the angles of attack, and then the percent chord cut. Explain what that is as well. So just a quick background, this is my senior design project. It was a replacement of the Boeing 767-300ER. Here are the customer requirements that we had to meet. For our senior class, we were broken up into teams like 4 to 6 people, and we had a semester to iterate through our design process to achieve these customer requirements. And as you saw in the previous slide, there was a significant amount of requirements, and they probably equate to a similar task as what I had here. Here's a list of all the different types of software that we had to use in order to achieve our customer requirements. Obviously, this is a lot of software to learn in a semester, so I think part of the task was to accept that each individual person couldn't learn each software, so one of us had to stop and learn each one, and then we'd all tie it together using Model Center, which you see down there in the bottom right. That tool's main purpose was just to dynamically update variables between software. So the point of this is I propose that I can handle a similar task in SOLIDWORKS with good design intent and taking advantage of parametric studies and flow simulation. Reason why I chose these two airfoil shapes are they're symmetric. They have a blunt nose that's symmetric on the top and the bottom, meaning I could replicate the cylinder. I could put a cylinder right there if I made a nice cut, and the geometry really isn't going to change dramatically. Now, as I make the percent cut, why I'm calling it that is right here based off of this pressure distribution plot. The highest pressure coefficient points are from roughly 2 to 6%, I would say. This is 20%. So those are going to be my starting points. I'm going to make a 2% cut of the chord. So if my chord's 200 millimeters and I'm making a 2% cut, that's going to be 4 millimeters. That covers the wings that I grabbed. Now the texture I want to test. I want to test a smooth texture, kind of a golf ball pattern, and then also I want to test shallow blades. Here's where the Reynolds numbers come from. If you go to the NACA, if you just Google search NACA 0012, there's an official website where there's these lift coefficient and alpha curves. There's drag versus angle of attack is what alpha is. This is just a good starting point for me to compare my results to. So I have 50K, 100, 200, 500, and 1 mil. That's what each curve is the Reynolds number, and then this is the lift coefficient and obviously alpha. These are the angles of attack. 20 might be a bit excessive. I realized that after I ran the studies, I could have probably stopped here, and investigated at 16, which would reduce the time it takes for my parametric study to run. All right, so next I'll show you how I took on this task with just SOLIDWORKS CAD modeling and flow simulation. So the input variables I went with were 10 degrees Celsius, and then I set my pressure to 942 Pascal, which is roughly at an altitude of 2000. And then using an equation in an Excel sheet, I was able to calculate the velocity based on the Reynolds number of 50, and this will be just another variable, but this is where I'm going to start, is I'm going to start at a lower number of 50,000 for the Reynolds number, and that equates to about 23.6. The rotational velocity, so I gave the cylinder a rotational velocity. This is the rotational velocity that matches the oncoming flow. All right, the computational domain. I used periodicity to basically save calculation time. Since the airfoil is symmetric along the length, I reduced my computational domain down to 100 millimeters. That's what you're seeing here. This is 50 and 50 millimeters going each way off the center. So that'll play an effect. That's why you see the shallow blades I designed. They only span 100 millimeters because periodicity is just basically going to do a periodic computational domain out for the remainder of the wing on both sides. Okay, so I have a rotating region. I have 3 different options to use. I have averaging method, sliding method, and boundary condition. So the sliding mesh method is a more robust method, since this method assumes an unsteady flow field, making it available for transient solutions. The drawback of this method is that the computations are significantly more demanding of your RAM, where averaging approach is recommended to use as a good starting point for an analysis. It's a simpler approach, mainly because of the assumptions made about the flow field distribution. The assumption is that it ignores the rotational characteristics. What this means is that a majority of the flow enters and exits the rotating region axially. But the advantage of this assumption is that it is less computational demanding. So, considering the assumptions made by the averaging approach, I may not want to start with the averaging method and instead maybe use the boundary condition to start. And then, if I want to zero in on my analysis, we would go with the sliding mesh, which that would consider the geometry, like for instance, a golf ball texture or the shallow blades option that I'm using. And also, I'm interested to see how it takes the smooth texture as well. For the boundary condition, for one of the first preliminary studies, since that's where I'll start, when I set up my boundary condition, I put in a real wall, and then it's going to rotate about the z-axis. And I know it says 50 radians. That's just when I took the screenshot, but I did end up deciding on going with making the angular velocity match the linear velocity coming at it. The next thing is going to be the goals. I have this equation here. It's really not even that bad, but I can make it even more simple in the software. I can take the dynamic pressure Q here and replace it in this equation and use that as one variable in the software, as one goal. I can set one goal to measure the dynamic pressure, which will get rid of all these variables. I also used good design intent and took advantage of the bounding box that I had set up to be able to calculate area. And then also I set a global goal to measure the lift or the forces in the y direction. So I did that, and then I used a equation goal to use all those variables together in one and estimate it for me as it calculates through. I'll start with the dynamic pressure. Click edit definition here. And so when I edit the dynamic pressure, there's this little dot here that's on the front plane. So I selected the front plane, and that basically is going to be, I just picked a point that was far enough away from the wing and ahead of the flow so that it would give me a good rough estimation of the dynamic pressure. So there's dynamic pressure. This next one, the surface area, that was a little bit more tricky. But let me just click edit definition so you can kind of see there is an option for CAD area right here. So CAD area, it's hidden right now, just so it doesn't look confusing, but dynamic surface area is what I named the body. And as you can see here, I set up a sketch that I'll get into that basically dynamically updates as the angle of attack changes. So as I change this number, angle of attack, the tail drops down, making this length longer. If I come here to custom properties and select configuration specific, notice I have total bounding box. Let me just make this wider. Length, width, thickness, and volume. So looking at these values, I know this 43.28 is going to be the shortest value, but that's my thickness, the one that I want. So cool little note that I did find out, if you're going to reference a bounding box in your dimension, you just get rid of the SW dash and just use total bounding box thickness. So let's see what that looks like. And that will pull that value. So double click that there. And I just click equals, quote, total bounding box thickness, end quote. And then it's going to set that value to my total bounding box. So as this bounding box updates, my surface area updates, and I can use that in a parametric study. So as I change the angle of attack, I don't have to worry about the surface area updating. Pretty cool. All right, again, so I was able to reduce down the equation, the lift coefficient equation here, to just lift over dynamic pressure times area. Again, there's the dynamic pressure and how I calculated the area. Also, I did set the length to 100 millimeters, or the computational domain, just to keep things simple. Again, taking advantage of the periodicity when setting up the computational domain, I took that into consideration when creating all the geometry moving forward. All right, so different options for meshes here. I was focused on the leading edge, so put a local leading edge mesh here just to basically wrap tight around. But as you can see, you're going to need to refine the mesh here to capture some more accurate data as it goes around this cylinder. And I'll probably need to open that gap up too. That's what I'm saying after I've run this study multiple times here. Then also I wanted to focus on the trailing edge local mesh. So I put in a little trailing edge there. Notice this is at like 0 degrees angle of attack. And then there's also this equidistant local mesh. So if you guys aren't familiar, equidistant's a pretty cool one to use, but I will say this does quickly make your mesh size very large. Here's where I have the trailing edge and equidistant and leading edge. And notice they're different colors. Trailing edge right now, I currently have it suppressed, and same with equidistance, mainly because it takes a long time for the study. But how you add an equidistant, I'm just going to leave this one here. Right click, insert local mesh. When you insert a local mesh, there is the equidistant refinement. So pay attention to these as I update them. So if I update this to 3, notice I have 3 squares, and then this is going to be the small square. So each value has to be different. So maybe the smallest square, since I know my gap here is 0.2. So maybe I'll make 0.2 my smallest, and then I'll just increment it up to 10. That's pretty large. 5 millimeters, and then the next biggest one would be like 10. So that might be a way you want to set that up. And what that looks like would be here. So these are going to be the smaller ones. This is only 2 levels, not 3. But this would be the in this case the 2.2 millimeters, and then this would be the 5 millimeters, and then you know this blue area could be the 10 millimeter in height. And then I wanted to suppress these again when I run the parametric study. That way I can look for a trend in the parametric study. All right, so I did a quick little comparison for smooth surfaces, golf balls, and shallow blades. So I did the boundary condition, averaging method, and the sliding method. So it was something that I found interesting was the curve for the calculations as they were converging for the lift coefficient. This is the lift coefficient conversion curve as it's running through the calculations. The boundary condition and the sliding mesh look very similar. The difference in the boundary condition, it doesn't consider the geometry. So I would assume these values would be very similar, but they're significantly off. And then also the progress, just kind of threw that in there if it's showing you how quickly it's how much it's progressed as it's converging. So I had 2 options for my calculation method: either let it run for 2 seconds. Actually, when I ran these, I had too many options, but realistically, I'll show you what I'm talking about. What I'm talking about is the calculation control options. Then if I come here, my criterion to stop one is for once one is satisfied. So typically, in this case, I want to have physical time of 2 seconds with a step size of 0.01. Basically, that means it's going to run for 200 iterations. If it hits 200 iterations, stop. Otherwise, if it converges, then when this lift coefficient converges, then to stop, because that's what's important to me was the lift coefficient. And then also I've noticed as I was running these, sometimes it may have a hard time converging based on the variables I had set. Maybe the Reynolds number is too high, so it's just giving me inaccurate data. So I'd stop at 200 iterations, kind of a thing. Notice how some of these flags here are red and one's black. Why is that? Well, here's why. Only one goal here is in the goals criterion. So as I check this off, that's why this one's checked. That's going to be the one that's going to be converging. So it's just a nice little way without having to pull this up to see which one's important to whoever designed. If you're getting into helping somebody out with their flow simulation, maybe you can be like, oh, this is what's important to them is the lift coefficient. All right, so this lift coefficient is significantly high, and I ran all these at 4 degrees angle of attack, which I don't know if you recall that from the previous slide, that's way too high of a lift coefficient. These are probably closer to reality for the lift coefficient of this. This is going to be the NACA 0015 at an angle of attack of 4 degrees at a Reynolds number of 50,000. All right, here's the golf ball. Again, I was getting weird values. It was only 24% complete for the averaging method, I would probably have to let this run for a little bit more time to get more accurate results. But the boundary condition, again, 48% through the calculation, same as the sliding method. And also the lift coefficients now are a little bit closer when we started throwing a little bit of geometry into the surface. Same thing with the last one. We got the shallow blades. We have the lift coefficient for sliding mesh and the CL. Seems to be a bit more stable of a curve, similar to the boundary condition sliding mesh method. And as I can see here, boundary conditions is significantly higher. To me, after seeing all this data, just quickly glancing through it, I think I know I want to go with the shallow blades, simply because that's the largest lift coefficient value that I was getting from all these. If I was, to move forward with this, I think for my parametric study, my first parametric study that I'd want to be running for a while would be the shallow blades, probably angles of attack from 2 to 16. Get rid of the 18 and 20 just to save some time. Also, something I've learned too is that this 501 mil Reynolds number is just too large, and I haven't really got a chance to play around with the percent chord cut, but I will show you how you can add that into a parametric study. We started with all these variables, and what does this equate to in SOLIDWORKS using design intent and the parametric study? I have two different CAD files for the NACA 0012, 0015 geometry. I have the variable angle of attack, which that gets played into down here for my parametric study. When you have a study that you've been running and you think you got it zeroed in and now you're ready, you click new parametric study. I already have one, so I'll just click open. These are my input variables. So I can select a dimension, and I'll I'll remove this dimension here, and I'll remove all of them just so you have a quick idea of how easy it is to add these variables. So to add a dimension, I'm going to select here, add dimension, and I'm going to select this angle of attack, and then I'm going to click the green check. Then if I want to add a step size, notice I have different options. This is this step around, and then we have range with step. That's the option I want. So I'm going to start at 2, then like I said, probably go to 16 degrees just because I don't need the extra calculations all the way to 20, and a step size of 2. And I'll click OK. So that's going to add 8 new studies. Next, I want to add in my variables, like initial condition of my velocity in the x, because I want to vary that velocity for the Reynolds number of 50, 100, and 200. I did say 501 mil, but again, I'm not really interested in that value anymore for this particular study because it's a little bit fast, probably for this wing design, and I was getting inaccurate results. All right, so this is at higher Reynolds number. So this is 50, 100, 200, and then 500 and 1 million. So those are actually going to need supersonic flow, and that's another option I'll need to turn on. So if I want to measure those values inside a SOLIDWORKS flow simulation, I'll probably create a new parametric study and vary the setup so that it can better calculate supersonic flow. But these seem, just at first glance, I can double click on this and quickly take a look at these pressure plots and see, oh, okay, that looks about right. But then if we get to here, get to this one, like, oh, there's some interesting stuff going on here. Again, this is a great place to start. I ran my parametric study, noticed this, that's why I stopped. I was like, oh, wait, that's not giving me accurate results. I don't want to run through the rest of these design points with that input or that output variable. Okay, so there's my first input variable. The next one is the rotating cylinder. The rotating cylinder here, that is linked though to the linear velocity. So as the linear velocity increases, the rotational velocity increases. So how do we do that? How do we add in that extra variable? Well, let's take a look. So I'm going to go here again and click add simulation parameter and then scroll down. And if you have rotating regions turned on in your study, then it'll pop up over here. And then if you have an angular velocity, you can select that and pull it in. So now there's my angular velocity. There's still two separate line items. So what I'm going to do is hold down Control, select both the options, and then I have this option to combine them. So I'm going to select Combine, and now they're 2 and 1. So let's go over here, and I can add in the rest of my variables. 47, 0.2. I'm just going to put some number in there. I can't remember what it was. 6820 point something. And then the next, I can't remember what that one was either. I'm just going to put some arbitrary value in there. For now, I think the other one was 94.4, but you get the idea. Then I'll click OK, and there's my variables. But notice it's only three added studies for the parametric study. So now I got two variables tied into one. They're going to update on their own. But let's quickly go back here as well. And I'm going to go back one more slide. I do have the percent chord cut as another option. So how do I add that one in? I'll just click over here. There's add dimension parameter. Now I'm just doing this to show you guys how to add it. I don't recommend adding a variable that is attached to a global variable if you're going to vary it. If you're going to change it here in the parametric study. This is 200. The chord is 200 millimeters. Easy number. I use an easy number to multiply it by 2%. Would be 4 millimeters. So the next one would be 3% times 200 millimeters. So that's going to be 0.006. 4% would be 0.008, 5% would be 0.01, and so on. So I can add in more, and now I have 4. So what does this look like for the scenario? I'm going to get this little pop-up because I had different values. These are my values here, my velocity that I'm taking in, and then my angular velocity that's paired with the linear velocity here. Then down here is going to be that percent chord cut. But it's asking, do you want to reset the scenario? Yes, that's fine. So it resets it. And now, just with that, I have 96 different design points. So basically what I found is a good place to start is to reduce your mesh down, your global mesh, when you're running this parametric study. So let me just pop this up. So I took my global mesh down to like 3 or 4. Also, I suppressed the trailing edge because I had to create a demo body to move with this chord line as it went down to update the trailing edge, and that was just a lot going on. And then same with the equidistance, it got to like 2 million for the mesh size, which was just ridiculous per study. I have the angle of attack, the percent chord cut, and then that's just the chord length, so you know. And here's how you vary all those in a parametric study. To handle the 3 different surface textures, I have 3 configurations. So this is going to be my smooth, golf ball, and shallow blades. And then as you see as well, I did averaging sliding boundary condition, and that's how I organized my study. And each one of those can have a parametric study. But my process is I was going to create an run each different type of study to see which one I wanted to go with. For my parametric study, I zeroed it in and I wanted to go with the sliding mesh study with the shallow blades to see if I'm going to get the maximum lift coefficient per angle of attack and Reynolds number. Since our labs have been down currently with our situation with COVID-19, I was able to utilize all 8 of our machines to run the study, to run different parametric studies, but due to human error, I had improperly set up my study, so essentially the results that I was coming up with were impractical. But on a bright side, I was able to stay late enough to see a good sunset here in Arizona. So from our Mesa offices, from our training lab, so that was pretty cool. Thank you all for attending today. If you have any questions, please feel free to shoot me an email at acook@goengineer.com. Again, my name is Alec Cook, and I am an application engineer for GoEngineer.